Right now we want to come to a new topic, our last topic for engineering mechanics. It's a very important topic. It's about bending of beams. And I think all of you already know the beam, this element, because we were dealing with this element during the last part of the first half of our course. During statics, we were dealing with the slender element beam, which can transfer not only a load along the beam's axis, so not only the normal force, but which can also transfer forces perpendicular to that axis. It's the so-called shear force and a so-called bending moment. And we know that there is a relation between the shear force and the bending moment, because if we would integrate over the shear force, we can calculate out of this the bending moment. Keep in mind that we started in many cases with some distributed load, some distributed shear force. So it's the unit of Newton per meter, and this was called small q of x. And then if we want to calculate the shear force out of the small q of x, we simply had to integrate over our beam to get this q of x. And keep in mind that also some discrete forces, which could be some external loads or also some bearing forces, had to be taken into consideration. And then we had this simple formula where we said the shear force is the negative integral over the distributed line load minus all discrete forces acting there. And in this equation on the right side, you see the Macaulay bracket. So that means we only have to take into consideration forces at the positions where they are acting. So if the expression within the Macaulay brackets is negative, then you do not have to take them into consideration. And if it is positive, then it is necessary to keep them in mind. And you could say this is just a jump function. So if the Macaulay expression is negative, then no consideration, and otherwise it jumps downwards with the amount of Fc at this position xi. Yeah, and the next step to get from the shear force to the bending moment is simply a further integration, so an integration over the shear force itself and minus all discrete moments which are acting with respect to the y-axis at their position. So same way as to integrate the discrete forces for the shear force. Here you have to subtract all discrete moments acting at their specific positions. As already mentioned during the first half of the course, we had our coordinate system where this x-axis was along the beam, the z-axis was pointing downwards, and the y-axis was coming out of the plane. That is the reason why the shear forces are influenced by this forces Fc, so the forces which are perpendicular to the beam itself, and the bending moments in our planar example are then the moments with respect to the axis which is perpendicular to the drawing of our system. So far, this is just to calculate the shear force and the bending moment, so nothing new so far. And what you can see in our equations, we use here a definite integration, so we integrate from 0 to the position x, and this x would be then from 0, so the start of our beam, to the length of our complete beam. But of course, what is also possible is that you make an indefinite integration scheme and then identify via the boundary condition. So that means q at the position x equals 0 has to fulfill a certain boundary condition, which could be calculated out of the equilibrium for our beam. And then you would have, of course, the same way to calculate the shear force and the bending moment. So there are two different possibilities, either the definite integration scheme, which is given here. That is the reason why I use this x bar instead of x for the integration variable, or you could choose an indefinite integration, so without the start point and the end point of your integral, so just without the 0 and x, and then write q of x dx instead of q of x bar dx bar. It's up to you. For all the problems we had in the first half of our course, it was possible to determine the bearing reactions out of the equilibrium on our beam before making any integration. And keep in mind what we did all the way is if we had a line load, we substituted this line load by the resulting force, meaning the integral over the complete line load. So the area which is covered by the line load is identical to the amount of the equivalent force, and the point of action or the line of action of that force crosses the centroid of the area which is covered by the line load. And by this method, it was possible to determine all bearing reactions in advance and then use these forces and moments in our integration scheme, where we had here the discrete forces, also the bearing forces, and the discrete moments, which would also be the bearing moments. But right now we come to our new topic, which is bending of beams, so mechanics of materials. And in this case, there might be systems where you are not able to determine the bearing reactions in advance. So it might be possible that you could just set up for your beam 3 equations, so equilibrium in horizontal direction, sum of forces in x direction, equilibrium in c direction, sum of forces in c direction, where you would have the shear forces, and equilibrium of moments with respect to the y-axis, where you would have the bending moments, and of course the influence of the shear forces as well. So 3 equations for your beam, and it might be the case that you have more than 3 unknowns out of your free body diagram. For statics, so for the first half of the course, it would not be possible for you to solve these equations, but for elastostatics, mechanics of materials, we get additional equations because there is a relation between the bending moment and the deformation of the beam. It's similar to the, keep in mind, the first topic we had in mechanics of material, where we had the tensile bar. There you could say that if you apply a force, you get some elongation in your bar, and if your system has more bearing reactions, so more unknowns, than equilibrium conditions you could set up out of the statics, then there is maybe a link between the deformations and the forces which are acting there, and you could set up additional equations to solve for all the unknowns. And for the bearing of beams, it's more or less identical to the tensile bars. So what is the additional equation you could set up? It is given here. There is a relation between the bending moment and the slope of your beam. So the not the change of the position itself, but the slope or the deflection, the change in the deflection line. And if the deflection is called W, then this W prime is just the derivative of W with respect to X, so with respect to the position we're looking at. So the inclination angle is somehow linked to that, and this equation can be calculated out of some model assumptions where you have a linear ansatz in this case, and yeah, what you have to keep in mind is that there is this M, so this is this bending moment, and this leads to the deflection or the inclination of your beam, and in front of this W prime, which is the derivative of W, there is this E times I, and E is something we already know out of the tensile bars. E is a material constant, so Young's modulus, so elastic constant, which is dependent on the material. So if you have, for example, a steel, it will behave different to a wooden beam or to a plastic beam or something like this, and you could look this up in some textbooks. And this I, yeah, this is the variable we already determined. It is the static moment of inertia, the area moment of inertia, and in this case with respect to the y-axis, as we only apply a bending moment with respect to the y-axis. So this was our last topic we were talking about. We said that not the area is enough to determine some resistance against the bending moment, but it's somehow how the mass elements are distributed over the cross-section area, and this is described by this I, by the area moment of inertia. In this case, as we are only dealing with planar bodies, so with planar beams, we do not have to consider this IC, so the area moment of inertia with respect to the z-axis, and we do not have to consider this IYC, so the area moment of deviation. It would be necessary to include if you were dealing with spatial bodies, and if there is not only a moment with respect to the y-axis but also with respect to the z-axis, then this could be a little bit tricky, but for our course we make it quite simple. There is only a planar beam and only moments with respect to the y-axis. Yeah, and as already mentioned, this equation is just a model assumption that there is a linear behavior between the deviation of our beam and the bending moment. And using this equation, we can solve for the deviation or for the curve, so for the change of the position, this W, because we simply have to integrate over the bending moment to get the derivative of the change of the position in z direction. And yeah, this is then just one integration method where we have this W prime of x equals minus 1 over E and I, and then we have in this case an indefinite integration in contrast to the definite integration we had for integrating over the line load or the shear force, m of x dx plus, and as I use here indefinite integration, I need of course this c1, which is then a constant, an integration constant, and has to be determined out of the boundary conditions. So this c1, if you assume the position x equals 0, so the beginning of your beam, then the integration, this term would vanish, and you would have w prime at the position x equals 0 equals c1. So this is exactly the slope or the inclination of your beam at the beginning, so at x equals 0. This negative sign, due to the fact that there is here in this expression this negative sign, it comes out of the coordinate system we are choosing. So if you have a positive moment, then your beam would try to get bended upwards, and upwards would be in the negative z direction. That is the reason why we have a negative sign. Just use this negative sign and don't miss it in the exam, because then you would lose a credit for nothing. So it's just to keep in mind that you have a negative sign if you go from this small q to the capital Q, and once again negative sign if you integrate over the bending moment to get the derivative of this W. Yeah, and if we are interested in the W itself, so the shifting of each element at the position x in the z direction, then of course once again an integration has to be used, and in this case once again I use an indefinite integration scheme, so I need a further integration constant c2, which can then of course be identified out of the boundary conditions as well. So w at the position x equals 0 would mean in the beginning of our beam what is the change of the position in z direction of the beam. And if you have, for example, a fixed bearing or pinned bearing or loose bearing in the beginning, then this C2 would be simply 0. Yeah, as already mentioned, we can easily identify this C1 and C2, which are the deflection or the derivative of it at the beginning of our beam. But as I mentioned, in some cases you might need further equations to solve for the unknown bearing reactions, and this can be done by finding additional points where we calculate some boundary conditions, and out of these boundary conditions we can solve for additional unknowns in the forces or in the bending moment. So in this case it would be recommendable not to solve for the unknown bearing reactions in advance, but to determine the unknown bearing reactions out of boundary conditions. And of course this depends strongly on your system, what you have, and has to be taken into consideration. What I already told you is that in some cases it's necessary to use boundary conditions to identify integration constants or unknown forces or bearing moments. And This is a very easy way to get credits during the exams and is necessary to solve the problems. So let's look at some simple examples. They are identical to the examples in the formulary, and I assume that Alex also talked about it during the lecture, but just to explain it once again, because this is really necessary. So let's start with the first problem where we have got our beam here. So we are looking at the beginning of our beam, so at the position x equals 0, and there is a so-called free end. Free end is a definition which was asked from some of you via email, as we already talked about it in the first half of our course, so for the bending of beam. A free end is, to be exact, an end of a beam where there is no external force or moment acting and where there is no bearing or something like this. So if you have some shear force, some bending moment, some normal force within the beam, and the beam then ends with a free end, there is no possibility that a force or a moment is transferred to the environment. You can only transfer a moment or a force to the environment if you have a bearing. So then this is really a connection between the beam, your system, and the environment. And in this case, you would not really speak of a free end, but there is, of course, a bearing which could transfer a moment or a force or both of them. And there is no force acting here. So that means, or a moment, a discrete force, a discrete moment, an external load. So in this case, we would speak of a so-called free end. And that means that the normal force at that position, in this case at the position x equals 0, would be 0, as well as the shear force and the bending moment. So this is the definition, the real definition of a free end. And as there is no possibility that there is something transferred to the environment, and as there is no normal force or shear force, still there is the possibility, of course, that the position is somehow deflected, so it moves upwards or downwards. So in z direction, it could move upwards or downwards. And there is also the possibility that there is some inclination of the beam at that position x equals 0. So if you assume that it's just a deflection line, and then of course would mean this, you cannot say in advance that this w equals 0 or this w prime equals 0. So you cannot state anything in advance concerning the deflection or the inclination of your beam at that position. So that means you can set up boundary conditions for kinetics, so for the forces and the moments, but you can not set up geometric boundary conditions, so meaning the deflection or the derivative of the deflection of the beam. Let's come to a second interesting example. It would be a loose bearing. So here you can see this is our loose bearing. That means it has the beam has the possibility to move horizontally, but has no possibility to move vertically. And that means that there is a force which prevents the vertical movement. So the force in z direction can be transferred to the environment. And because of this discrete force, this bearing force in z direction, we cannot state in advance a relation that Q, the shear force at this position, in this case x equals 0, would be 0. That is not possible, because the shear force at that position is identical to the negative bearing force. That is what we can state. But we cannot say this Q equals 0. But what we can say is that the normal force at that position is 0 because there is a free sliding possible, and as there is a free sliding, there is no bearing force in axial direction, so in x direction, in the direction of the beam itself, which prevents this horizontal sliding. And if there is no bearing force in horizontal direction for our loose bearing, yeah, of course, the normal force has to be 0, otherwise this would not work anymore. And we have this free rotation for a loose bearing, therefore also the bending moment at this position is 0. So two possible statements for kinetic boundary conditions, what we already know out of statics, and now for mechanics of materials, what are the kinematic, the geometric boundary conditions? Yeah, let's look at this point here. This bearing point, as already mentioned, prevents that the point is moving upwards or downwards, and this movement upwards or downwards is described by this W, so this W has to be 0. The point stays at the at this C position, does not move upwards or downwards. But of course, it is possible that there is a deflection of our beam in this position, and that would mean that we cannot say anything on the derivative of the deflection. So the inclination is not necessarily 0. That means we can once again state 3 boundary conditions, 2 for the forces or moments and 1 for the kinematics. A similar example would be then a pin bearing. Pin bearing in this case allows once again a rotation with respect to the bearing point. So this means that the moment at this position is 0. Yeah, it can rotate with respect to that point, but the point itself cannot move horizontally or vertically. If it cannot move horizontally or vertically, then there are forces which prevent the movement. So there is a horizontal force which prevents the movement to the left or to the right. And of course, this horizontal bearing force has to balance the normal force within the beam. So we cannot state a boundary condition for the normal forces. It could be an arbitrary value. So you could state that the normal force at the position x equals 0 equals minus the bearing force in horizontal direction, but you cannot state that it is 0. And for the shear force, it's the same. So this pin bearing has the possibility to transfer a force in vertical direction, in z direction, and this shear force then is minus the bearing force in z direction. So once again, no possibility to state here a boundary condition equals to 0. And for the kinematics, compare it to the loose bearing, it's identical. So the position remains at the c coordinate position, so w equals 0, but still there is the possibility that we have an inclination of our beam at this position, and therefore this w prime is not equal to 0. That is the case if we look to the next problem. Here we've got a fixed bearing. So fixed bearing means that there is really a rigid connection between the environment and the beam, and that means that there is no possibility that the beam moves horizontally or vertically, and it cannot deflect at the beginning, so there is no inclination angle possible. In this case, we would have an inclination of 90 degrees, and this would not change if you apply a force here. So that means, out of this definition of the fixed bearing, not only this w equals 0, but also this w prime equals 0. And as already mentioned, this prevention of w and w prime means that you could have normal forces, shear forces, and bending moments which are transferred via this bearing type to the environment. So if you would make a free body diagram, you would enter here a force in x direction, a force in z direction, and a bending moment, a bearing moment, and they would just balance the internal loads of the beam at this position. So that means, to sum it up, for a fixed bearing, you could only state two equilibrium conditions, two boundary conditions, and in this case only kinematic, so geometric boundary conditions. And this will be helpful for solving our problems. As already mentioned, for the beginning of our beam, in many cases we already know what are the boundaries, but what we also should look at especially is the end of the beam or any bearing point you have where you could state additional conditions, and out of these conditions calculate for the unknowns. At this point I want to stop and wish you a nice lunch break. Hopefully you have prepared all the relevant questions so that we can discuss them during the afternoon session after we have solved the 3 remaining problems on bending of beams.